Kinematics is the study of motion. So if we want to study the motion of, say, a car, the first step in any kinematics problem is to decide how to put down your coordinates, choosing the coordinates. You can't talk about where the car is if you don't put down some reference point to measure everything from. So, for example, if I'm standing here watching the car, I might make my x-axis begin at this point. However, someone else who watches the car from the starting line might make that their axis beginning over here. Either one is a perfectly fine x-axis. Notice one thing though. This person is going to say the car starts here at t equals 0. I would say the car starts over here at t equals 0. Now, what that means is my starting time for this observer would be t equals -4 seconds. -1, -2, -3, -4. There's nothing wrong with t being equal to -4. Time can absolutely be negative. It just means that it's before this person's stopwatch began. That's all it means. We can absolutely have time be negative. Okay, so we have to choose our coordinates. The natural choice given this picture is to make this person the observer and put their x-axis down starting from there. So let me erase. So we'll make that the starting time at t equals 0 when it starts at the left at position 0. So in other words, our x-axis starts there, the origin's on the left side, and runs to the right. The car is shown every second. From that, we can plot a position versus time graph. Position on the vertical axis, time on the horizontal axis. Shows us where the car is at any given moment. Now, what things can we learn from a position versus time graph? Well, the first thing we can figure out is average velocity. Average velocity is just the change in the x-coordinate divided by the time interval. So for example, I could find the average velocity between 2 seconds and 5 seconds. I take delta x over delta t, and you know that's just the slope of the line between those 2 points. That's the average velocity between 2 and 5 seconds. Okay. Also, you know the instantaneous velocity is the velocity at a single instant, and that's when you take the time interval between the 2 points to be infinitesimally small, and that's just dx dt. Remember when finding velocities that you can always go back to units to remember the equations. Velocity is meters per second. And so you're always going to be taking something in meters divided by a time interval to get velocity. Now, what in this case, the car is not changing its direction, so the velocity is always positive. What about if the velocity changes from positive to negative? For example, what if our graph looks something like this? Position versus time. And what if the slope changes? So here it's a positive velocity, and then the velocity goes negative, something like that. Now, we can figure out average velocity, instantaneous velocity in exactly the same way, but what about the average speed? Suppose I want to know the average speed from, say, 1 second to 5 seconds. You cannot just take average velocity and take the absolute value. Okay? Average velocity is the slope between the 2 points. Like that. That would give me the average velocity. That's not what I want. I want the average speed. In order to do average speed, you have to take the total distance that it covered and divide that by the time interval. So the distance means how far it goes to the top of the motion. So here's the peak of the motion right here. You have to take this distance, d1, plus this distance, d2. Why is that not just the same as delta x? Well, because delta x counts d1 as positive and d2 as negative. Average speed, you just take the distance, the scalar distance, not the displacement, but the total distance, d1 plus d2, both positive numbers, and add them up to get the distance. Divide that by the time to get the average speed. Next is a velocity versus time graph. In this case, the car is increasing its velocity. We call that a positive acceleration. It's actually gaining speed. Then it maintains a steady velocity for a few seconds. That's zero acceleration, no change in the velocity. Then there's a negative acceleration where the velocity is dropping from 8 meters per second down to 0. Now, careful, on this stage, the car is just slowing down. It's not that it's headed backwards. The velocity is just decreasing. So it's a car that speeds up, cruises, and then slows down. Negative acceleration doesn't mean negative velocity. It means the velocity is decreasing. Okay, so what are the things we can learn from a graph like this? Well, first there's the average acceleration. The average acceleration is just the change in the velocity over the change in time. So, for example, I could figure out what average velocity the car average acceleration the car experiences from 3 to 9 seconds, and I'd have to take the slope like so. That's the average acceleration. You take the change in the velocity over the time interval from 3 to 9. There's also the instantaneous acceleration. The instantaneous acceleration is dv dt. It's the slope at any instant. So if I want to know what the acceleration is at 5 seconds, the slope there is exactly equal to 0. Remember to think back to units. If you don't remember how to calculate these things, acceleration is meters per second, meters per second squared. And that means you have to take meters per second divided by seconds to find these quantities. So always go back to units to guide you. From a velocity versus time graph, we can also figure out the displacement, how far it goes. What you have to do is remember that dx is equal to v dt. In other words, to get meters, you have to take meters per second times time. Now the velocity changes, so this just tells me the tiny little bit of distance covered in a tiny split second. These are infinitesimal distance and time. I want to know the total amount of distance over some span of time interval. So you integrate on both sides. The integral on the left side gives me delta x, x final minus x initial. The integral of the right side is the integral from time 1 to 2 of v dt. The point is, I can find displacement from time 1 to 2 by looking at the area under the velocity graph. So for example, I can find the displacement of the car from 7 to 9 seconds. I just have to look at the area of the velocity graph from 7 to 9 seconds. So I'm looking at this area here. That gives me delta x. You'll get a positive number for delta x because the car is actually heading to the right from 7 to 9 seconds. The velocity is positive, it's just slowing down, but it's still covering a stopping distance as it decelerates. Now we have to be more careful if the velocity goes from positive to negative. For example, our car here speeds up, then cruises, then it decelerates and goes down to 0 velocity. But that deceleration continues and the velocity goes negative. So it's a car slowing down, immediately throwing it into reverse and heading backwards. Now it's negative velocities. Then the car hits a peak speed in reverse of minus 40, and then starts slowing down to 0. Notice the car is not going forwards here. It's still negative velocities. It's still in reverse, but slowing down in reverse, finally coming to rest. Okay? Make sure you listen to that many times if it's not clear that from this whole portion here, it's going forwards, and on this whole portion here, the car has negative velocities and is going backwards. Make sure you're not mixing up acceleration and velocity. Okay, so in this case, the velocity goes negative for a portion, and so we got to be extra careful about distinguishing displacement versus distance. Okay, for example, suppose I want to know the displacement of the car from 20 to 40 seconds. Well, the rule is you have to look at the integral of the velocity graph from 20 to 40. But notice from 20 to 40, there's a positive area. From 20 to 30, then from 30 to 40, the area goes negative. Positive area and negative, and in fact, the areas are identical, so there's 0 displacement from 20 to 40 seconds. How does that make sense? You see, here the car was slowing down, then it throws into reverse and is heading backwards. So at 40 seconds, the car is at exactly the same place as it was at 20. At 20, it was headed forwards. At 40 seconds, it's heading backwards, crossing the same point. So the displacement between 20 to 40 was actually 0. It doesn't mean the car didn't go anywhere, it just went out and back to the same place. So if you want to know how far it went out and back, you have to look at the distance covered between 20 and 40. Then you'd have to take the distance number 1, that's this one here, d1, and add it to the distance d2, looking at just the absolute values. So then you'd add both triangles up, ignoring the fact that one of them is negative, to get the total distance out and the distance plus the distance back again.